Good students, welcome to International Brain Excel School. This is the physics class and our topic today is elasticity. Elasticity. Now, when talking about elasticity, what comes to your mind? Any material that stretch and that's straight. Alright, but for us to understand elasticity, we must first understand what we refer to as rigid body. Now, what's a rigid body? A rigid body is a body which 2 points in that body are invariable. That is, a rigid body is a body that does not succumb easily to deformation. So anybody that does not subject easily to deformation is what we refer to as what? Rigid body. Now, whenever we subject a body to deformation, the body tends to regain its original shape or size. Alright? Whenever we subject a body to a deforming force, the body tends to regain its original shape or size. Now, anybody which has the tendency of regaining its original shape or size after being subjected to a force of deformation is what we refer to as what? Elastic material. Is what we refer to as elastic material, or you call it elastic body. So anybody that regains its original position after being subjected to a force of deformation is what we refer to as what? Elastic material. Now, there are two extremes when we're talking about any material. All materials form in between two extremes. They form between the extreme of elastic, perfect elastic, and what? Perfect plastic. Perfect elastic and perfect plastic. So all materials forms in between this point. So all materials form in between a perfect elastic material or a perfect plastic. Now, what's a perfect elastic material? A perfect elastic material is any material that regains its original shape or size immediately after the force of deformation has been removed. So the moment you remove the force of deformation, if the body regains its original shape or size instantly and it regains it perfectly, then you refer to that body as a perfect elastic body. But we are talking about a perfect plastic body. A perfect plastic will never regain, is going to maintain its altered shape or size after the force of deformation has been removed. So a perfect plastic will maintain its original, its altered states, its altered shape or size after the force of deformation has been what? Removed. But a perfect elastic will regain its original shape or size after the force of deformation has been what? Has been removed. So I said that an elastic material is any elastic material or elastic body is any body that regains its original shape or size after the force of deformation has been removed. Now, let me say something about the force of deformation. Now, if you hold an elastic material in your hands, you are going to discover that there is a potential energy that is stored in that elastic material, and the potential energy stored in any elastic material is always equivalent to the force of deformation. For example, now what I'm trying to say is that the potential energy stored in any material will equal to the force of deformation that is stored, alright, that you are going to it will equal to the force of deformation that the object can be subjected to. For example, now, if the force of deformation acting on a particular object is around 10 Newton, alright, the force of deformation is around 10 Newton. Now, the work that will be done in overcoming that 10 Newton force of deformation will also be what? 10 Newton. And that 10 Newton that we use to overcome it is what you refer as our resistance force. And that resistance force is stored in form of energy, in form of potential energy in your what? Elastic material. Alright, so that is that about elasticity. But there are two important terms that we must be familiar with anytime we are dealing with elasticity. Two most important terms. One, we have stress and strain. So we have stress and strain. We have stress and strain. We have stress and strain. Now let me start with strain. Let me try to draw a spring here. Now let me draw a spring here. Now, please get this explanation. Now, a spring is an elastic material, or any elastic material you can find in your hands. Maybe a rubber band, something. These are elastic material. Now, by the time you apply a force of deformation to this elastic material, you apply a force of deformation to this place. Now, the force of deformation you apply will do what? Will pull the object down. Now, by the time it pulls the object down, there is an internal energy. Or let me say that internal force. The internal force must be overcome in order to pull this object down. Now, let me give an illustration. I apply a force of 10 Newton to this thing, a load 10 Newton to draw this thing down. Now, the internal force will also increase to 10 Newton. If the internal force does not increase to 10 Newton, it implies that this body, after the force of deformation has been removed, will not be able to regain its original position because the net force will not equal 0. But if the internal force, which can be called a resistance force, is equal to the force of deformation, it implies that the net force in this system will equals what? 0. Now, if this net force equals 0, then the body will be in a state of equilibrium. Now, what then is your strain? For us to divide our strain correctly, we must understand that we have 3 types of strain. 3 types. And these types of strain that we have is dependent on the state of matter. It's dependent on the state of matter. Remember that we have 3 states of matter: solid, liquid, and what? And gas. But let me make it this way: 2 majorly. We have solid and we have fluids. Now, when you're talking about solid, an elastic solid can change in 2 ways. Number 1, it can change in shape, and it can change in size. Do you get that now? It can change in shape and it can change in size. But we are talking about a fluid can only change in volume. And volume deals with what? It deals with size. A fluid does not easily change in shape, but it easily changes in what? It easily changes in volume. An elastic material, so it is very easy for us to have fluid elasticity only in terms of volume. But when it comes to solid, a solid can be elastic either in form of its shape or in form of its size. So with this now, we can say that we have 3 types of elasticity. 3 types of elasticity. How many types? Sorry, 3 types of strain rather. How many types of strain we have? 3 types. We have 3 types of strain. 3 types of strain. Number 1 that we have is that we have a tensile or longitudinal strain. Tensile or longitudinal strain. So number 1, we have tensile or longitudinal strain. Number 2, we have shear or shearing strain. And number 3, we have volumetric strain. Alright, so we are talking about tensile or longitudinal strain. What are we talking about? Longitudinal means, number 1, we're talking about tensile strain. Our tensile or longitudinal strain is talking about length. And we must understand that generally our strain is expressed in terms of what? Is expressed in terms of ratio. Our strain is expressed in terms of ratio. So we're talking about tensile stress. We are talking about it's dealing with what? Length. It's dealing with what? Length. So tensile strain deals with what? It deals with length. Longitudinal strain or tensile strain deals with length. And I said that our strain generally is expressed in terms of what? Ratio. Now look at this. Let's assume that we have a particular elastic body. This way. We have an elastic body this way. Alright. Now by the time we apply a force to this thing, we subject this to a force, we discover that the length, which was at this point before, let's call this please L1. Alright, which was at the point L1. By the time we apply a force, we discover that the material has moved to this point. So let's call this place from here to here, let us refer to it as what? L2. So which implies that from here to here is our change in length, right? You want to give us L2 minus L1, which is our change in L. So let me go to small letter L for that one. Why I use capital for line. Alright. Which implies that our tensile strain can simply be defined as the ratio of change in length, to original length. Alright, the ratio of change in length to original length. Let me use change in length to what? Original length. Alright, so let me use small letter L for change in length, and let me use capital letter L for original what? Length. So that's our tensile strain. Change in length over what? Original what? Length. And since our tensile strain is expressed in form of ratio, it implies that our tensile strain does not have any what? Unit. Because the unit of length here is meters, and that equals 1. So it implies that our tensile strain has what? No unit. Has no unit. So when you're talking about tensile strain, it deals with what? Size. And the size we're talking about is just one dimension, which is simply what? Length. Now, number 2, we have shear or shearing strain. Our shear or shearing strain deals with shape. It deals with what? Shape. It deals with shape. So our shear or shearing strain deals with what? Shape. Is that clear now? It deals with shape. So how do we explain that? Now let's assume that we have a particular shape. Let's assume that we have a particular shape. Let's assume that we have a particular shape in which we want to look at critically. Now, critically looking at this object in front of you, I'm using R as an object. Alright? Okay, now let us take this place as the original point. Now, if I apply a force, remember that she was standing here. Alright, look at my hand. Class, everybody, look at my hand. Just standing here. Now, if I apply a force, a small probe, do you see what happened? She has moved from this point to what? To this point. A little shift. Now, this change in shape for any object is what we refer to as what? Shearing strain. Alright, the ratio of this change, alright, when two surfaces, alright, move, when two layers move over one another, alright, is what we refer to as what? Shearing strain. Thank you. Alright, is what we refer to as shearing strain. Alright. Now, our shearing strain has to do with what? It has to do with shape. Alright, number 3 is volumetric strain. Is what? Volumetric what? Strain. Volumetric strain. From the word volume. So our volumetric strain is simply the ratio of what? Change in volume to what? Original volume. The ratio of change in volume to original what? Volume. The ratio of change in volume to original volume. So let me use small letter v for change in volume, and let me use capital letter V for original volume. So the ratio of change in volume to original volume is what we refer to as volumetric what? Strain. Is what we refer to as volumetric strain. And since it is volume, it also has what? It has no what? It has no unit. 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 Alright. I won't explain the three types of strain that we have. This one deals with what? Solid. This one deals with solid. This one deals with fluid and what? Solid. Now, this one deals with size. This deals with size. This with the shape. Size, shape. Size, shape. So shear or shearing strain deals with the shape, while tensile stress or volumetric strain deals with what? Size. Thank you. Alright. It is also imperative for us to understand that we also have three types of stress. Now, every strain is accompanied by a corresponding stress, and every stress is accompanied by a corresponding strain. You cannot have strain and not have stress. You cannot have stress and not have strain. Wherever you see stress, there is a corresponding strain. Wherever you see strain, there is a corresponding stress. Because every stress will cause strain, and every strain will cause stress. Which implies that our tensile or longitudinal strain is caused by tensile stress. Our shear or shearing strain is being caused by normal stress. Our volumetric strain is being caused by what? Tangential stress. It's being caused by tangential stress. It's being caused by tangential stress. So we have three types of stress. We have tensile stress, normal stress, and what? Tangential what? Stress. Three types of stress: tensile stress, normal stress, tangential stress. A tensile stress we call tensile strain. Normal stress we call shearing stress. A tangential stress we call what? A volumetric what? Strain. What then is our stress? Our stress is simply the ratio of force to area. Our stress is simply the ratio of force to area. Stress is simply force over what? Area. Now, our force is measured in Newton. Our area is measured in meter squared, which implies that the unit of stress is Newton per meter squared. The unit of stress is what? Newton per meter squared. So wherever you see stress, you see a strain. Wherever you see a tensile stress, you see tensile strain. Normal stress, you see shearing strain. And tangential stress, you do volumetric strain. Let me say something about normal. The word normal is a mathematical word, which simply means what? Angle 90. Alright, it simply means perpendicular. So look at the board. If I stretch my hand to the board, you can see my hand is making a right angle with the board. You can see that my hand is acting normally. So when you apply a force to a particular surface in all directions, alright, acting normally to the body, you claim to have a normal stress, and that will lead to change in what? In shape. Alright, so I believe that you understand our elasticity, then you understand stress and strain. In the next class, I will proceed to other subtopic in this place. Thank you so much. Stay safe.